All right, let's get right into it. Today we're decoding the mathematical engines actually running our modern world, finite automata. We're going to start with those everyday systems we all just kind of take for granted, and then really zoom in to the deep theory powering them behind the scenes.
I mean, have you ever actually stopped to wonder how a vending machine tracks your exact change? Or how a traffic light flawlessly sequences its colors day in and day out? We interact with these things every single day, right? But beneath the buttons and the blinking lights, there is this incredibly rigorous mathematical blueprint. So let's explore how evaluating these specific problems actually reveals the hidden logic of our tech.
So here is our roadmap for today's analysis. First, decoding finite automata. Second, DFA and NFA models. Third, conversions and reductions. Fourth, Moore and Mealy machines. And finally, applications and limitations. Okay, starting off with section 1, decoding finite automata. So the crucial takeaway here is that these abstract machines essentially serve as foundational language acceptors and verifiers. You can think of a finite automaton, or FA, like a highly disciplined, completely humorless gatekeeper. You feed it a string of information, say a password, and its literally only job is to evaluate that input and make one definitive decision, accept or reject. It's the ultimate verifier, and really it functions as the fundamental building block we use for evaluating complex problem statements in computer science. Moving right along to section 2, DFA and NFA models. Now, this is where we see a really sharp contrast. DFA, which stands for deterministic finite automata, is incredibly strict and predictable. For every single state and input, there is exactly one guaranteed path. No surprises, but NFA, non-deterministic finite automata, it's vastly more adventurous. It can actually have multiple branching paths for a single input, or, get this, sometimes transition like magic without any input at all. That's what we call an epsilon transition. Now, intuitively, you would probably think the NFA, with all its flexible, non-deterministic branching, would be way more powerful than the rigid DFA, right? But in the mathematical universe of finite automata, they actually possess entirely equal power. Any language an NFA recognizes, a DFA can recognize too. So the internal processing might look totally different, but their ultimate capability as language acceptors is exactly the same. Let's jump into section 3, conversions and reductions. Because DFA and NFA are perfectly equivalent, we can actually seamlessly translate between them and regular expressions. It's essentially a complete ecosystem. You take a theoretical regular expression, convert it into a flexible NFA. Then, transform that NFA into a strict DFA. And to close the whole loop, you can convert that finite automaton right back into a regular expression. But here's the catch. Once you convert an NFA to a DFA, you very often end up with a bulky machine just packed with redundant states. So by evaluating alternative methods for FA minimization, we basically act as editors. We strip away the excess to create a reduced DFA. And in the real world, this crucial step saves precious memory and CPU cycles, which is exactly what makes your models computationally elegant and highly efficient. Next up, section 4, Moore and Mealy machines. So up until now, standard FA just accepts or rejects. But these finite state machines, they actually take action. The distinction here is simple, but it's massive for system design. With a Moore machine, the output depends strictly on the current state. But with a Mealy machine, the output depends on the current state plus the current input. Exploring these functional design alternatives is absolutely essential when you're constructing dynamic state-based systems. And just like DFA and NFA, Moore and Mealy machines can actually be converted into one another too. The catch here is that you have to meticulously verify and validate that conversion through rigorous testing. But if you do it right, it guarantees that whatever design you ultimately choose for your real-world system, its functional behavior remains perfectly intact. Which brings us to our final part, section 5, applications and limitations. This is where all this theory actually comes to life. In software, compiler design relies heavily on finite automata for lexical analysis, basically teaching a computer how to group the raw text of your code. And in hardware, Moore and Mealy logic is exactly what allows a traffic controller to safely manage a busy intersection or a vending machine to finally drop your snack, but only after it sees the exact right combination of coins. But as powerful as they are, finite automata have a fatal flaw: finite memory. They literally cannot count to infinity, and they cannot remember an arbitrarily long sequence of previous inputs. So I want to leave you with this final thought. When a real-world system eventually requires infinite memory tracking, what happens when the logic of finite automata simply isn't enough? What heavier, more complex computational models must we build to bridge that gap where FA ends?